Okay, for real this time. We are going to talk about narrowband IoT very briefly, which is sort of appropriate for the technology. It's it's a very constrained bandwidth technology. So today we announced that we're giving out 3 things. So I should start by saying that this is a pilot program that we're running. All of you have access. It's not generally available yet. I'll talk a little bit at the end of today about the steps that we'll be taking discreetly between now and general availability. You should all hopefully have been given one of these. And in here you have sensors and hardware and a sim and everything that you need to get started and all of the instructions that you need. And actually, the way we're going to start today is just by setting one of these up. We're just going to see how it works, do a little demo. And so let's kick off by doing that. You guys are all, is anyone not familiar with this thing? So this is like I remember like, this is like first coming to the United States. I was like, wow, that's the dumbest thing I've ever seen in my entire life. It's just a button that Staples sells and you press it and it says that was easy. So we're going to build the world's first internet connected, I'm making that up, but it could be the world's first internet connected easy button, and we're all going to participate. But we're going to start by just working through the whole narrowband setup. Drew, my colleague, is going to help here because we need to parallelize things even more now than we did before. So I should point out that the odds of this demo working perfectly the first time used to be very low, and now they're yeah, whoever said 0 is like pretty close. They're approaching 0. My first step is I just go in here and say I want to register a SIM. When you're in programmable wireless, you can order or register SIMs. When you order more than 10 SIMs at once, we put them on your account automatically so that you can configure them before they arrive. But there's a different type of SIM that we call a starter SIM, and that has a code on the back. And so I'm just going to type in my code here, which is great. So it's just created my SIM for me, and I give it a unique name. So I'm going to call it Narrowband Meltdown. And what you'll see is that I get given what's called a rate plan. So Twilio, we let you create your own rate plans. We don't let you set your own prices just yet, but we do let you decide on what types of services will be available to your SIMs. Now, narrowband, right now at least, you don't really have many options. You need data enabled, and you need messaging enabled. And there's no voice, and we'll get into why there's no voice later, but narrowband as a technology actually doesn't support voice. And there's no national or international roaming either. And we can, if we have time, we can talk a little bit about why that is as well. But basically, it's just early days for narrowband. So I'm going to click through here and just activate my SIM while Drew goes and sets everything up. And I lost my IDE before. That's good. That's not good. Okay, 1 second. Fix it, fix it. Okay, this is super disappointing, but so because I had to reboot my laptop, the sketch that I was working from, I don't have a backup of, which is great. So what are we going to do, Drew? We're going to do this demo slightly differently. We're going to do we have the backup? Yep. Yeah, okay, cool. Always have a backup, I guess. Basically, we activated the SIM. It's all active. We put it in the device. Actually, the device will come online now. The sensors that you have with your kit, you have temperature and humidity, you have ultrasonic range, which detects distance, and then you have a button. And we're going to use our button, but we have to use it on the kit that we already loaded the software onto when we were preparing for this. So that's okay. It'll still work. But what I want y'all to do, if you can, is to send a text message to this number. And you can send anything you want. Is anyone getting a reply? I gotta run my code. Yeah, which is export. What is it? Okay, cool. I'm sorry, can I get you all to text a message to this number? This is going superbly well. Okay, so you'll get something back that says live demo, fingers crossed. I think it's a little too late for that. Joking. Okay, cool. And now the idea is this is hooked up to the Narrowband network. Was it that one? This one is turned off. Oh man, this is... All right, we got totally derailed here from the start by this stupid power problem, so I'm just going to talk about Narrowband. I'm so sorry. Drew's going to fix that while we talk about it. That was not easy at fucking all. That was... Are you sure that's the right one? All right, let's try this. I'm going to press this button. If you get a call, put your phone on speaker. I don't think that's the right device, Drew. I really don't. Okay, we're going to move on. That was really hard. And we're not even going to talk about those. Okay, so... Anything? Okay. When we talked about Narrowband earlier today, we talked about it as being low cost, low power, self-service access, and then, of course, this developer kit. Again, completely derailed just now by some upfront technical issues for the demo, but we can do it again later, maybe. Yes, put it on speaker. So you get what it was supposed to do, right? Okay. That sound is gonna haunt me. So what actually happened? Okay, if everyone could hang up just to stop. Oh, look, my phone's ringing. I wonder who it could be. Yeah. Okay. So we all texted to Twilio. Twilio sent those messages to my code running on my laptop via HTTP. And then the device, again, couldn't get my code onto the new device, but we put it onto one that was already running. Hit the button. It travels to Twilio via UDP. Twilio hits what's called the commands callback URL on my laptop, and then my laptop punches back to Twilio and says, hey, call all those people and tell them about how easy it was. So that's what was supposed to happen. Let's move on. So I want to spend a little bit of time just talking about what makes Narrowband low-cost, low-power technology. We can start with the power side of things. So there's three things on Narrowband technology that can make it more efficient. From a power perspective, there's radio optimizations. You may have noticed that it's called narrowband. You're probably familiar with the term broadband. Narrowband is essentially the opposite. There are sleep optimizations, which is really related to how the device is connected and listening to the network at any given time. We'll talk a little bit about those. And then there are data optimizations, which relate to how data is actually communicated on the network. And then once we talk about Narrowband a little bit, we'll just talk about our Narrowband product, where we're taking it, and I kind of want to do the demo again, but I think we're going to run out of time, but we'll see. So let's talk about radio optimizations. A normal LTE band, as in the amount of frequency that it takes in the universe, is pretty large. The smallest LTE band size is 1.4 megahertz, 200 kilohertz band for narrowband. And so what this means is you have a very small amount of space that you're communicating in from a radio perspective, and that sort of constrains what you're able to do with it, but it also makes it a lot more inexpensive to deploy. And so we can talk a little bit. Are people still getting calls from that app?
Just getting the calls.
That's awesome. Oh, a lot of people must have texted in then. That's great. I can kill it. Okay, it should be dead now. It should have been dead a long time ago. There's three ways to deploy narrowband. There's in-band, which just means we're deploying narrowband in the same radio space that we're deploying LTE. This is what T-Mobile is doing right now, but they have plans to do things differently. Then you have guardband deployment. Guardband deployment is you have two normal LTE bands. They have a little bit of space between them so they don't collide with one another. And because narrowbands are so narrow, you can actually deploy it in the guardband. So it means that we can deploy capacity without actually spending essentially any more money on spectrum. I like to think of the metaphor here as like in California when the motorcyclists drive between the cars on the freeway, only less annoying. And then you can also deploy it into what's called standalone mode. A narrowband band happens to be the same size as what's called a GSM channel. So you can repurpose 2G networks for narrowband to get greater, density utilization out of those. And so two points to make here. One is that we're talking about less radio space, which is going to save us money. Save us energy inherently by not having to listen across a broader radio space, but also because of the deployment options, this is one of the things that means that we'll get to see large density and low prices. What the industry targets is 50,000 devices on every city block, and so in order to do that, you have to be able to deploy this stuff pretty widely. Then there are what we call sleep optimizations, which really relates to how your device actually connects to the network. So you may never have thought about this before, but the cell phone in your pocket is not constantly listening for things. It has a timer in it, and the timer is very small. So the phone in your pocket is probably listening to the network every 1.28 seconds, something like that. And what we can do with narrowband and with some of the other low-power wide area technologies is change the way that we listen to the network for content that's coming down to our devices. And this is a really dramatic way of being able to improve battery life. Now, there's a downside to this, which means that narrowband and some of these other technologies like LTE-M are not great for all types of use cases. But for some use cases, it really doesn't matter. So we'll talk a little bit about use cases later, but narrowband is particularly good for sensor networks, for things that detect something and then send it up. And the reason for that is that it doesn't want to always be listening for whether or not it needs to know about information that's coming down. So the first sleep optimization is called power saving mode. Power saving mode, the device essentially tells the tower, hey, I want to go to sleep for this long, and when I'm done sleeping, I want to be awake for this long. And the tower will say yes or no. And you can negotiate these up to quite a big period, which is on my notes, which are not on the screen because of all of this stuff. I'm actually just going to fix that right now because that's really easy to fix. Ready? Oh, something worked. Okay, so power saving mode, a device can sleep for up to what? How is that even possible? It's just a laptop presenting on a screen. Do you guys see nothing? It's showing on my laptop that the screen is still plugged in. Oh. Okay, cool. Yeah, awesome. This is smooth sailing. A device can sleep 4 up to 413 days, which is a really long time. Pretty cool. This is making me bananas. The gentleman in the front has a Windows laptop that I can borrow. Okay, we're just going to go back to mirroring and see if it helps. Do you get anything now? Oh, man. I did come to the tech check at 12:30, by the way, and everything was swimming.
This one is going to be forcing it.
Okay. At this point, I'll just turn my laptop around and.
You got it.
Oh, you got it?
Okay.
Woo! Okay. So one of the good things about power saving mode is it improves the density of devices on the network because you have this little tiny band of bandwidth to share. But if you're not all constantly reserving time on it, then you can actually shove quite a lot of devices on it, which is another thing, of course, that brings down price. The other sleep optimization that we have here is called EDRX. EDRX stands for Extended Discontinuous Reception. And this is more like what your phone's doing. So your phone has this paging window down the bottom left of every 1.28 seconds. Sometimes it's every 0.64, I believe. So literally every 1.28 seconds, your phone in your pocket is scheduled to turn on and listen to the tower and know if there's anything coming for it. With EDRX, we get this concept of a hyperframe, which is specific for IoT. And so we can basically negotiate with the tower to listen at much longer repetitive intervals. And we can actually negotiate to listen between every 20.48 seconds to 175 minutes. So why would you ever use this when you could use power saving mode? Well, the answer is that when you're in EDRX mode and you're scheduled to be listening on some regular basis to the network can actually cache information for you. So the network can essentially store very small packets of data for you, and then you don't have to go into transmit mode to receive them. You just have to go into listening mode. So every, whatever it is, 21 seconds, 175 minutes, device perks its ears up. Is there anything waiting for me? If so, it can turn itself on and do something different. If not, it can just carry on with its life. So EDRX mode is sort of better for use cases where you don't necessarily know if you're going to be receiving data. You may have something like a HVAC system that every morning at a certain time receives its instructions on what temperature to set a building to. That would be a better power saving mode use case, but EDRX would be better for, say, maybe something like a sprinkler system that gets turned on and off at will. The third category of optimizations is what we call data optimizations. So we're all, I'm guessing a lot of people in this room come from like web, mobile development backgrounds. Probably a lot of folks who are building things have only ever built for IP networks. And that makes sense. IP networks obviously dominate the world. The downside is when you start talking about like very, very small packets of data. So let's say you have, to my previous example, an HVAC system or a sprinkler system. It's probably in your best interest from a power perspective to come up with your own sort of binary encoding scheme for exchanging information and actually use very, very, very small packets of data. And so this is an illustration of what happens if you use MQTT and TCP to communicate a 5-byte transmission repeatedly. You end up with basically your device is spending all of that blue bar to communicate headers, so to negotiate IP and to send IP addressing information and then to do TCP keep alives and all that kind of stuff. And then the actual 5 bytes of data, which is the, hey, this is the temperature right now or whether the sprinkler's turned on, actually only ends up in this orange box. And when you're plugged into a big, heavy battery or when you have mains power or something like that, this is not really a big concern because it turns out that this stuff's a lot easier to work with. The efficiencies that we get are better. It's super reliable. It's super scalable. But when we're talking about devices that have small batteries or that we want to deploy somewhere far away from society or somewhere where we don't want to go and change the battery all the time, it becomes worthwhile for us to take advantage of these optimizations that I'm about to talk about where we get rid of all of this stuff and we do what's called non-IP data delivery. And so what non-IP data delivery is basically you can exchange information to and from devices in the signaling channel, in the same channel that SMS uses, but basically in the signaling channel of the cell phone network. So you never establish what's called user plane connectivity. You just basically, in addition to your normal signaling messages, hey, I'm awake, or I'm trying to connect, or whatever it is, you actually just throw little tiny packets of data into that channel, and then that allows you to save a lot on battery. There's two things that, so those three optimizations that I talked about, radio, sleep, and data are the main optimizations, and the outcome is something that looks like this. So there's two things that will affect your battery life. There's the actual amount of traffic that you're sharing. I stole these slides from Biology, from T-Mobile, by the way, so thank you, Biology, well, this one in particular. There's the amount of traffic that you're actually sharing on the network, and then there's the think of it as like the struggle, like how hard it is to transmit that based on the coverage that you have. And so in optimal conditions where you are not using a lot of uplink power, and where you're not really, actually, even when you're transmitting more frequently, you're going to get this 10 years of battery life that we talked about in the keynote this morning. The main predictor, actually, of battery depletion, if you look at this, is how much uplink power we're using, which is really a function of interference. It's a function of distance to a tower. It's a function of maybe capacity or over provisioning on a network. So the RF conditions are certainly the most important thing that we keep in mind here, as well as the traffic pattern. So that's power. We also talked about low cost. The costs from Narrowband are driven by a few things. So we talked in the keynote today about hardware. Narrowband is what we call a half duplex technology. It's not a full duplex technology, so it can't upload and download simultaneously. It may give you the illusion that it can because you can switch between the two very quickly, but it can't actually do both at the same time. But what that means is you need half as many antennas, which makes your device quite a bit cheaper. And then there's some other reasons, commercial reasons and otherwise, that the chipsets are actually a bit simpler, a bit more free from some restrictive licensing, and so the chipsets get a lot cheaper as well. Connectivity gets cheaper for a number of reasons. One, mostly it's the stuff I talked about just now, which is better density on the network due to these sleep optimizations and the guard deployment and just using less bandwidth, basically. So where we're at now with our pricing is this. We are shipping a developer plan. The developer plan is $2 a month. There's no minimums. There's no really anything. You get 12 megabytes included. No, you don't. You get 2 megabytes included, and your overage is 5 cents per 100 kilobytes. That sounds expensive, but these devices do use very little data. The reason that the developer plan appears to be quite a bit more expensive than these annual plans, we'll talk about annual plan, is the developer plan allows you to have a lot more connections per day. So in the annual plans, we do have this notion of, it's sort of like an acceptable use policy at 10 connections per hour. It's not to say that devices will be automatically shut off or anything like that. It's just to say that if there's a device that's radically drifting away from the mean and using too many connections, that we sort of reserve the right to give you a call and talk about how to resolve it. So that's the annual plans. Annual plans starting at $10 self-service and coming down as low as $5. And then the number that I mentioned this morning was $4. That's our lowest price. The $4 price is a 5-year plan. So we think this is where most people will land for production devices for large deployments. 5 years, 100,000 plus devices, and we're talking about $4 a year per device. And that's not a gigantic deployment in the sense of what we're talking about here, which is massive IoT. So I touched a little bit on use cases when talking about how the technology works. The technology, like very clearly, you're not going to have mobile phones running on narrowband. I also mentioned that voice doesn't work, and I mentioned that the devices are half duplex. That's the reason. There's other reasons. The bandwidth is very low as well, but you can't actually do real-time communications without full duplex, because if you're uploading something, then everything else is going to be blocked from coming down. So connected car, mobile, wearables, these are more real-timey use cases. You also probably don't want to be, for example, with a wearable, maybe in the situation where you can't be constantly listening for new traffic that's coming from the network. So the perfect narrowband use cases are things like environment monitoring, things like a button when it works, where it's not actually listening to the network all the time, but as I press something, I can go and take an action. Smart buildings, smart city. Smart city is probably where we see the most utility for a technology like this. So monitoring buildings, monitoring parking spaces, monitoring almost everything. It starts to get really interesting, I think, when you go beyond the notion of, okay, I can interact with an individual device because it's connected, to the point where, like some of what we start to see now, where we have some ride-sharing networks, for instance, where they're turning their devices from not just being a bicycle, but being an environmental sensor at the same time, that's sharing data, that's giving it to the city. I think some of the coolest use cases will be in terms of how we make stuff more magical in the city with the data that we're able to collect by connecting devices. There are some use cases like tracking that are not ideal for narrowband. However, you can do them. Narrowband lacks a concept of what is called active mode mobility. Active mode mobility basically is when your phone hands off from one tower to the next. It doesn't need to renegotiate a lot of stuff. It just sort of hands off. Narrowband supports idle mode mobility, but not active mode. So it's not perfect for tracking, but quite honestly, you're still probably going to get better performance out of it than you would out of some of the existing technologies. It's just not exactly what it's designed for. Okay, so our product. I was going to talk a lot about this in the context of the demo while we were waiting for things to work. But basically what we've shipped is we've shipped this developer kit today. We've shipped an Arduino library for it. It's currently just Arduino. And we are talking to our cloud services today over the internet. And then the messages reach us, we process them, and we've exposed a very straightforward user interface to developers, which is called our Commands API. Today, the Commands API is used for machine-to-machine SMS. So all it really does is very straightforward two-way messaging. Send a message, receive a message. It doesn't have any sophisticated queuing. It doesn't do anything that you would find in a product like Azure IoT or AWS IoT or anything like that. So that's where we've started. We've started by just saying, okay, we're going to do low-power communication on and off the device, but it's going over the internet. It is DTLS encrypted, coming to us. We then have that plugged into our Commands API, and you can hit that with using HTTP, and that's how eventually, somehow, I managed to press that button and get that call to come through. Call to go out, I should say. So the next things that we want to do are, we want to do away with that internet interface between the T-Mobile network and us, and that's something that we'll do before we make this thing generally available. And what that means is that you'll get the smaller, the more efficient use of the network that we talked about with the non-IP data delivery. Also simplifies the solution. It means that you no longer are using DTLS, which can be a little bit chatty in terms of message counts. So we think it's going to be pretty good from an energy saving perspective. We want to expand our module support. So today this board has a uBlocks N410 module on it. That's the only module that we're supporting with our code that we've released. It's also the only board that we're supporting right now. We want to expand that. Where we'd really like to get to is just to be able to support all of the modules that T-Mobile has certified for their network. And we'd like to get it to a point where it's not an Arduino library as such, but more of just a C, C++ SDK that you can build onto into whatever platform you're working with. If you're using free RTOS or whatever it is, you should be able to work with that. And then the third is this expanded cloud IoT service support. So again, today we're just exposing this very straightforward HTTP two-way messaging, send a message to your device, receive a message from your device. Not very opinionated, short messages. You can encode them as text, you can encode them as binary, but it's pretty limited. The next step will be, okay, well, how can we make sure that on the southbound side of Twilio, we're talking to the devices as efficiently as possible using these somewhat special knowledge cellular technologies like non-IP data delivery that we talked about. But how can we actually surface that on the northbound interface of Twilio and make it so that that works with whatever you're already using today? So if you're using Azure IoT or AWS IoT, whatever it is, how can we bridge those two things? And we think this would be a really good scope for a general availability release. In the meantime, we're going to continue releasing. Everything is on. I was going to show you, but I'm not even going to try and do anything. Everything's on GitHub, so it's there. You can work with us on it. We'd love your contributions. The only one other thing that I want to talk about while we're here is that we did announce two things today. So we announced SuperSim, which Andrew just talked about in the previous session, and this is Twilio's long-term platform for global IoT connectivity across all technologies. And then we announced Narrowband in partnership with T-Mobile. We would like to see a future where the SuperSim supports all technologies and where it works all around the world with all of those technologies. I have to emphasize that Narrowband right now is extremely new. If you're using the Narrowband kit that we give you, you're probably among the first people in the United States to ever use Narrowband for anything. And so there's some interoperability stuff to figure out there for the whole industry. There's no Narrowband roaming as it would be right now. And so it's specified but not implemented, we could put it that way. So there's work to do there. But I did want to just point out like how these two things differentiate from one another. Narrowband is US only. There's actually no Narrowband networks in North or South America outside of the US anyway, in terms of the actual radio networks. And it works on the T-Mobile network today. The T-Mobile network is deployed nationwide, so you can play with it when you get home. And yeah, SuperSim available earlier next year, and it'll be supporting 2G, 3G, and all the flavors of LTE when it lands. That's all I have for you.
Thanks, Evan. Thanks, everyone, for dealing with the hardware challenges. If you have any questions, Evan's going to be around. The rest of our team are going to be around. We're getting started again at 3 o'clock in this room, so stick around for getting started with Programmable Wireless with John and myself. Thanks.